Hi everyone and welcome to the webinar. I'm here today to talk to you about digital solutions for zero carbon. My name is Ruth Kerrigan and I'm the Director for R&D, and I'm here with my colleague Lorenzo De Donatis, who is one of our R&D consultants. I'm just going to give you a very quick brief intro to the digital solutions for zero carbon and who IES are and what we're trying to do to achieve this goal. And then I'll hand over to Lorenzo, who will take you through a case study of actual use. So who are IES? IES, we've been around for 26 years. Our software, the bread and butter of our software has been dynamic simulation modeling. In the early years, we were focusing on design of new builds and compliance and using the software for energy design. But in the last 10 years, through different research projects, we've been able to expand the software for master planning and urban design, buildings and energy management, and also resource management. And all of our softwares work together on a single collaboration cloud, so you can bring all the data from different aspects, whether you're looking at a new design project or an energy management project or perhaps an urban planning project or a network project, and bring all of that data into one holistic cloud-based platform so that you can make good decisions at city levels for decarbonisation and for different aspects that you want to do. And that's the main goal that we've been trying to achieve in the last 26 years, and to be able to help communities plan their operational performance better. One of the brilliant things that's kind of happened in the last number of years has been digitalisation of the built environment. And there's lots of technologies that are now being developed that are enabling our software. This market is growing significantly. Smart cities, smart initiatives, new technologies, digital technologies are evolving very, very quickly, and even 5 years ago we wouldn't have had some of the technologies that we have now that could enable us to do an awful lot more with respect to cloud-based modelling, data integration, data collection, etc. One of those, or two of those particular technologies, is IoT. A couple of years ago we were trying to get data from buildings, and we'd have to rely on the building management system, and sometimes we wouldn't be able to even get into that building management system. But now that we have IoT, they're quick, easy, wireless sensors. Costs are coming down, they can be relatively cheap now. And these can be placed in buildings quickly and easily to help us to collect data and understand how the building is performing in real time. This allows the growth of that energy management market. It also allows us to expand our software beyond just building energy and design. And this is where we come with our digital twin. So digital twins for zero carbon are, again, one of the hot topics of the moment. Buildings must become in complex network of services. A lot of the times there's no data, or there's lots of data, but there's no information. So we pride ourselves on turning that data into information. We also look at being able to model the building and understand those complex interactions. So what are those knock-on impacts with respect to both the building and the community, and making sure that we can identify those unintended consequences and look at the holistic picture of how the building works, but also works within its environment. The digital twin also, we can couple it with things like machine learning to be able to do further analytics and optimization, prediction, and beyond just what physics-based modelling can do. And lastly, we can help it to design renovation, retrofit, energy management, improvement scenarios, look at different OPEX, CAPEX savings, investment costs, and help people make the best decisions of what they're going to do, but also de-risk their investments as they go forward. And I think that's a really, really key part, is any decisions that we make for our built environment, we need to make sure that we are actually going to make a difference. And we need to make sure that we're going to maximise the investment for that building owner, but also de-risk that investment if they don't end up investing in technology that doesn't actually give them a return, especially if they're relying on those returns to pay back a loan for the investment of that technology. Where we see ourselves sitting in this market of the digital twin and our USP in particular, on the one hand we have the physics-enabled simulation software that we've had for more than 26 years. That's based on fundamental physics principles. It's been around for a very long time. It has a very good reputation in the market, and it's been proven. Now, as we said, through the evolution of IoT and BMS data being more readily available from buildings, we can augment that physics model with the real data to improve the physics model. On the other hand, we can also use the physics model to generate virtual sensors. which in turn allows us to reduce the number of potentially IoT devices that you would have to place in the building and reducing those costs. So both the physics model and the real and virtual sensor data, they work together, they augment each other, that we can actually create that digital twin of both physics model and real data. And then what we can do is we can add in the AI and the machine learning component. So if, for example, I have an IoT device that's measuring data at a 5-minute interval, but I have BMS data that's measuring at less than 1 minute interval, we can use machine learning and AI to fill the gaps, bring all of that data into the single model, and be able to look at everything in the one view and with the one time frame. Another example there would be a lot of the time you might have gaps in your data due to downtime from your Wi-Fi connection. The data's not actually been sent to the cloud, or perhaps the BMS hasn't logged it for a day or two. So again, AI and machine learning and with the use of regression algorithms, we can fill those gaps and create clean, full profiles of the data to then work with that physics-enabled simulation model. And we can also then use AI and machine learning for optimization, prediction, and training the data. And all three work together to give us what we believe is our USP with respect to the digital twin and what is unique to RES that no other company is currently doing at the moment in the market. And the last thing I'll just say is that when it comes to decarbonisation, there's lots of different things that we need to do. We've got this list of 8 items here. However, it's not a case of saying, I'm going to do 1, then do 2, then do 3. The whole point of this is that we might first want to look at low energy conservation measures, or a part of the city might be applying a deep renovation strategy, or another part of the city might be implementing some local production. The point is that these steps should happen at different levels, different scales, different buildings at all the one time, but we should be able to measure and verify and bring all of this data onto one single platform so that we can understand how the building and how the city is performing. And that's very, very important. So the top and the bottom end of this scale, for me, are the most important. If we don't understand our baseline, and if we don't understand how our buildings and our cities are performing in the first instance, then we can't create a good roadmap for how we're going to improve them. And going back to things like de-risking the investment strategies, you need to have that good baseline to be able to understand how you can improve, where you're going to get the maximum value for your investments, and how you're going to make sure that you actually achieve the savings that you're going to achieve. And that leads into the other end of the scale, which is continuous optimization and recommissioning. We can't do an approach of, I'm going to design a building, hand it over and walk away. We must measure, verify, commission, recommission all of our buildings across that built environment all of the time. Otherwise we'll end up with a built environment that's gold standard or NZEB or A rated on paper, but in reality we will not achieve carbon emissions that we set out to achieve. So that's me, and I'm going to hand over to my colleague Lorenzo now, who will take you through an example of the digital twin use for Limerick City in Ireland. Thank you very much.
Thank you, Ruth. Hi everyone. Basically, I now want to show a case study of one of the projects that to which we applied the concepts that Ruth just guided you through. So basically, this small case study that I will be showing you will show basically a part of the city in Limerick. I will just go on with the slides to give you an understanding on how the project looked like. So basically, we took the historical city center of the Limerick city. The idea was starting from the large scale simulation and then going through more detailed understanding on how the single buildings were performing. As Ruth said, it's important to start enlarging the scale of the building simulation to try to understand how to possibly decarbonize bigger districts and even cities ideally. So basically what we did was creating an energy model of the whole historical city center of the Limerick city. And you can see that our tool basically simulated the energy consumption of this whole district. And the idea is that all the information that we gathered were in terms of geometries, in terms of simulation inputs, were taken from the most accurate source of information that we had at the moment of the project. So, for example, the geometries came from the city itself that had all this information. Then all the input data came from statistics from the Sustainable Energy Authorities of Ireland. So all the information that we used for the simulation were retrieved based on either like sources of information or reasonable assumptions, for example, on the construction age of the building and so on. So after simulating the whole district and having an idea of what's the energy consumption and CO2 emissions of the whole district, we then focused on a single block, which is called that PEB there, which stands for positive energy block, because the aim of the analysis was taking a few buildings in this block, 5 buildings in particular, and making them positive, so consuming less energy than they are producing, so that the overall balance of the year will be positive. These are the 5 buildings that we took into account. As you can see, the bigger scale model is a simplified model, while for the 5 buildings that we took, we created a very detailed VE models. Most of you might be familiar with the virtual environment. So basically, compared to the community model, the VE model will be much more accurate. So we basically collected all floor plans, sections, additional information on the schedules of use of the buildings, and we created these 5 detailed models. And as you can see, the buildings are very different in terms of end uses, because we have educational buildings, commercial, residential, and so on. The idea was that once you have to create a positive energy block, so once you want to start sharing energy between the buildings, for example, we also looked at the possibility of installing photovoltaic panels on the roof of these buildings, and we will see the results afterwards. But the idea is that taking different end-use buildings, it will be easier and more reasonable to eventually share energy between buildings. For example, when a school is closed during summer, maybe the residential building or the office could be using energy which is produced by the other building. So the idea of having a mix of different end uses is also beneficial to the study that we were addressing. In this particular presentation, I will focus on how we created the model for that educational building there. And so in the next slides, I will show you how the so-called baseline energy model was created. So basically, the first thing will be collecting energy bills. So we collected utility bills for both electricity and natural gas usage of this building. And obviously, I wanted to take this building because it's a very real case scenario in which the utility bills were only giving results every 2 months, and even 2 months of a whole year were missing. So we did not have information on that. And this is very representative of a real case scenario, because when you are modeling a building, most probably you won't have all perfect information, all sources of information, how much insulation there is, or exactly how much this building is consuming. So this is a very good example. So 2 months of the energy bills for this building were missing. So the total energy consumption was about 130 kilowatt hour per meter square per year, which is obviously underestimated because 2 months are missing. And then there is split into natural gas and electricity, a bit slightly higher natural gas because the heating was through natural gas. The idea now is how to move towards near zero energy buildings, starting from this situation. So first of all, we need to build a digital twin of this building. So once we have the building, we start collecting floor plans, sections as much as possible, and we build an energy model of this building. So you can see there are 5 steps that we consider. The first one that we want to address is how to create the energy model. So you all know when we create an energy model, we assign a location to the model, some weather data. Here there is just very brief description on how the weather is like in Ireland. You can see that the heating degree days is basically the whole year and there is no cooling needed. And so basically, okay, you start creating and positioning your model according to an appropriate weather file. Then you need to start making either assumptions or retrieving data from sources. So basically, what kind of input, once I'm done with the geometry, I need to give to my building. You can see that the green ones are basically assigned as sources. It means that we were able to retrieve that information either from a site visit, so basically a building visit, or from SEI is basically the Energy Authority of Ireland, which has values according to the location and the construction date of that particular building. So this is more, when you see the green, is more, let's say, a reliable source that you can directly assign to the model. While the blue ones are the assumptions. So where, for example, we didn't have information on the roof type or on the ground floor, then we started only through the assumptions. So in this case, once again, the energy values from the SEI, but the site visit didn't allow, for example, in this case, to access the roof. So this remains as an assumption because it wasn't confirmed by a site visit. And the reason why it's important to understand the difference between source and assumptions is because when you start then tweaking the model, trying to reach the same results that your utility bills are suggesting, then it's, let's say, easier to start tweaking the assumption rather than the sources, because ideally the sources are verified, so you don't want to mess up with information that you know it's accurate. Now, other inputs after the building, let's say, envelope are obviously, as you know, the lighting, heating system, ventilation system, heating sources. So all the additional information that you need to give your model to run an energy simulation. In this case, we had fluorescent lights for most of the buildings. A few of them have been replaced with LED lights. We had underfloor heating system, a ventilation system which is mixed between mechanical and natural ventilation, and we had 2 gas boilers, and that's the reason why we had that high natural gas consumption in the utility bills. And then finally, the last inputs that we need to give to the buildings are obviously what are the thermal set points, what's the schedule of the building. For example, this was a special school, was not let's say a normal one, as so you can see there were many events. For example, during Thursday evening, there were many events in a particular room. So in the model, we needed to represent that somehow, and we gave to that particular room a specific profile. So you start from the very standard profile for a school, then through site visit, through interviews to the building owners, you start tweaking those profiles according to the actual building. So starting from a building standard or whatever it is, and then you start, let's say, increasing the accuracy of the model according to site visits, according to any information that really you can collect. And then infiltration and heat losses are based on the construction year of the building, because most of the times, especially in older buildings, they didn't perform any blow door test or anything that can give you an exact value of that. Now, so we assigned all the inputs to the building, but now we need to ask ourselves, okay, I run a simulation and I need to compare that with the utility bills. Utility bills data most of the times are coming, for example, here I copied from an Excel file that we received. They are every 30 days, if I'm not wrong. Yeah, monthly data. So monthly data are not ideal for a very high quality comparison. So what we do is basically, in this case, we were lucky enough to have the division, the split between day and night from the energy, from the utility bill itself. So basically what we did was importing this CSV into iScan, which is our online platform where we collect all data, and through basically merging the information from the utility bills and the schedule of the building, we were able to represent better what could be a consumption during the day. So you can see the time scale here is day by day. So every hour there is a different consumption. You can see at night is lower, but it doesn't go to zero because we had the information that there is consumption also during night, probably for appliances, refrigerators, and so on. So basically we started, let's say, extrapolating hourly data from these monthly bills, and then we started comparing that to the VE simulation, so to the model energy simulation. And this gives a much better representation on how the model is actually behaving, rather than like compared to just monthly data. And after doing this, so we here just a summary of how month by month basically the utility bills, which are the red values, are compared to the green one. So you can see that the simulated values, so the green one, are very much representative of the building itself. There is a peak here in May, which obviously the model didn't represent, because maybe there was some some special occasion that was like, I don't know, a week of full events or something like that. So the next question would be, for example, okay, let's try to understand what happened here. Was there a problem in the meter, or was there actually something happening? So you go on and you start calibrating that model better and better. And you can see here the simulated model was able to understand how much the building would consume during November and December, where the utility bills were missing. So the simulated model is able to fill those gaps that basically the utility bills were not covering. And once we did that, we did the same for the gas consumption. In this case, for the gas consumption, we were able to basically use some machine learning model that, based on the heating degree days of the location, basically represented better the value, because if we extract a single value, just dividing every day for the whole year, we will get the red value, which is basically a constant value for heating for a whole month, which doesn't make much sense. While using some machine learning algorithm, according to the outdoor temperature, to the heating degree days and non-heating degree days, we were able to actually modulate this consumption along the year, so to give more meaningful results to our utility bills. And once we did that, we were able to calibrate the building on the heating consumption as well. Just a quick example on another way of using, for example, sensor data to calibrate a model. And when I say calibrate, once again, the meaning is to try to have an energy model as much representative as possible of the real building. Another way of using this will be sensor data. This is not related to the same building, it's related to the residential building, because the residential building basically used sensor data for occupancy. So basically, let's say you start from a compliance profile for a residential house. This will be a normal compliance profile for an Irish residential house. But then in that particular building, we had CO2 sensors because the building owner decided to install CO2 sensors. And you can see that basically, if you plot a line on the average air CO2 concentration, which is about 400 ppm in normal condition, you can see that when basically this line is way above that, it means that for sure there is occupancy in that particular room. In this case, the mezzanine was that particular room. So using this information, we can go back and actually change that compliance profile to a so-called calibrated profile, because we are sure that here and in this particular hours here in this specific room, there will be no one according to the data that we have from the sensor. So the calibrated profile is for sure more representative rather than a standard profile that you assign to every room in your building, which is not representative of the real situation. And this is just a particular day of the year, but through our platform, basically we were able to quickly do this through the whole year and create a profile directly from the sensor and importing that through the virtual environment. So we created a profile directly from the sensor itself. This was just an example of another way to use that. So coming back to the educational building, this is the baseline energy consumption. After the simulation, you can see it's higher than the utility bills because there were the 2 months missing, November and December, which are quite high in terms of natural gas consumption. So this is the situation, the total energy and the split between natural gas and electricity of the baseline model. And now the next question will be, so how we move towards near zero energy building. The first step that we considered was operational measures. Operational measures are those measures that basically have a low effort, but can still have a quite good improvement. And a couple of them we considered. First of all, zone heating controls. The baseline building basically was heating all the rooms, even the unoccupied ones, at the same temperature, which was obviously not efficient. So we started saying, okay, let's use individual thermostats and heating set points based on the activity, because different activities might have different needs, and the occupancy. And let's use just a setback value of 16 degrees for the unoccupied rooms. There are basically here underfloor heating systems, so it's good to still have a setback temperature rather than switching off completely the system in this case. And you can see that on the right we have the energy consumption after the operational measure is introduced, and we would have basically 17.1% reduction, which is completely on natural gas, almost nothing on electricity. That 0.1 is just because of pumps that were running lower rather than in the previous case, but it's mostly on natural gas because this measure would affect the heating. And the next measure that we considered was reducing the domestic hot water supply temperature. Most of the times systems just supply temperature at 60 degrees. We realized that we could decrease that up to 45 degrees C, not less, because there will be Legionella problems with the Irish regulations. So we decreased that supply temperature with 45 degrees, and we're still able to provide that hot water as much as we needed. And you can see, obviously, this is a smaller reduction compared to the previous one, just 1.8%, but it's basically just a control on the heating system, so it's something very quick and easy to implement and no cost. So we have 1.8 reduction, while 19% if we combine this to the previous operational measures. So the two together would reduce 19% the total energy consumption of the building. And obviously, if only one measure would be chosen, the zone heating control will make the most impact. The next interventions that we started considering are the shallow retrofit. Shallow retrofit means that you are not actually doing a deep renovation, so you are not changing the whole aspect of the building, you're not changing an external wall or the roof of the building, but you are applying some, you still need some manual work to do those. For example, one of those are, the first one that we consider is improving the air tightness. As you know, older buildings are quite air leaking. So the infiltration rate, the initial one was quite high for every room. We were losing about 0.2 air changes every hour in the different rooms, and we reduced that to about 0.07, which is a good value because we don't want to go too low in an old building with a not perfectly efficient mechanical ventilation system. So we don't want to seal completely the building. Otherwise, we might have condensation problems, but still reducing by 3 times this value will bring to 6.8% reduction. So it's quite a good reduction considering that we only basically here sealed the doorways, the various let's say perimeters of the windows and so on. And you can see that the saving once again is mainly on the natural gas side here because we are reducing the needs for heating the space. If I go to the next one, the next intervention, which is nowadays quite considered, is the application of LED lighting, so LED lighting and daylight sensor control. This means that not only we replaced the fluorescent bulbs with LED lighting, but we also thought about implementing some daylight sensor control, especially on the rooms. As you can see from the building, we have we placed sensors in the model nearby all the rooms that are nearby the perimeter of the glazed perimeter of the building, so that basically the sensors from the model are telling us when there is enough illumination, when there is enough illuminance in the building thanks to the daylighting, and it's basically modulating the output of the lights from 10% to 100% based on the looks that we have on the work plane. Basically, this reduction will bring to, this improvement will bring to 1.7% reduction of the heating loads, of the, sorry, electricity loads. You can see in this case, it's reducing the electricity loads, and compared to the added, sorry, to the previous one, it will bring to 8.4 reduction of the overall measure. If you can see, if I go back, basically the previous one had 96.4 in terms of natural gas consumption, while this one goes up again about 102. This is because basically the LED lighting, LED lighting would increase the natural gas consumption in modeling terms, because we have less heat losses and heat gains within the building. So we need to heat up the space more. This is something that is interesting to actually understand when we will apply this intervention to the building and start looking at utility bills, because most of the times this increase won't probably be seen because people are not just increasing the set point because they changed the lights. So probably this increase here would actually not be seen at all because it's just a modeling effect, but probably this combined reduction will be even higher in a real case situation. And the last shallow retrofit intervention that we looked at was replacing the old boiler, so the current boiler, with a seasonal coefficient of performance of about 0.75, with a new one about 0.93. It's much better performing. And you can see there is a great advantage in terms of both electricity consumption and natural gas. So the electricity consumption is related to the previous measure. So you can see that overall the combined reduction is about 20.9%, while if we had only to replace the boiler, we still had 13% reduction. So if only one measure will be applied, this will be the best one in terms of shallow retrofit interventions. Last but not least, actually the most beneficial interventions are the deep renovation ones. So when you start actually addressing the presence of insulation in your building, replacing the windows and so on. This obviously had a very good saving percentage, but they come with higher costs. So in this case, it will be needed an analysis of payback time and so on to understand if they are feasible or not. So first of all, just a slide saying basically on traditional buildings, we even went to courses on specifically on traditional buildings, because not everything in terms of deep renovation intervention can be done in traditional buildings. There are a lot of restrictions, especially in terms of external envelope, a lot of things to be considered. For example, once we try to add an insulation, actually we need to take care about the possibility of condensation if there is not enough mechanical ventilation and so on. So for traditional buildings, there are a lot of guidelines that need to be followed, and as most of all, the building condition assessment and survey, because even after looking at all the guidelines, you still need to go to that specific building and see what's the actual condition of that building to see if an intervention makes sense or not. Some of the possible interventions that we consider were, okay, first of all, a roof insulation, which is the easiest part normally of the building, which can be insulated. Basically, the U value of the roof went from 2.3 watt per square meter Kelvin to about 0.6, thanks to the aerogel insulation material that we considered. And also this is reducing the air leakage of the building, because most of the air leakage is going through the roof. And this will reduce 2.9% the total energy consumption of the building, mostly on once again on natural gas consumption for space heating. The next thing will be internal wall insulation. It's slightly more complex, but if there is the possibility in a specific building, that's obviously one of the things that will reduce the most your heating loads, especially if the building comes with no insulation at all when constructed. And in this case, we reduced 21.4% the energy consumption of the building, and 25.2% if combined with the roof insulation as well. Here, compared to the previous shallow retrofit and operational measures, you can see that with deep renovation measures, when you start combining interventions, actually their combined effect is even higher than just summing up the single interventions, because when you start insulating the roof but you don't insulate the external wall, you are just moving your air leakage and your heating losses from one part of the building to the other, while when you start combining this intervention, then you really start seeing their benefit. And the same about windows retrofit. Basically, we had single glazed windows. We could use this solution, basically replacing the single pane with the double pane with the basically vacuum material in the middle of the two window panes. And with this solution, we won't need to replace the window frame at all. So the traditional aspect of the building, which most of the times won't allow you to replace the frame of the window, will still be untouched with this intervention. So we are really still replacing the window pane. And the fact that there is vacuum material rather than air is a solution that is convenient in this situation, because we are basically putting a new pane on the same previous frame. So there could be with time a little bit of gap. So if there was air or argon, even worse, that could leak. While if you have a vacuum material, if you have just vacuum between the two panes, you don't have any problem of possible gas leakage or any possible dangerous material, let's say. And this will reduce only by itself 4.5% the total energy of the building, and 32.2 if combined with the previous ones. You can see that it's going higher than just summing up the values. And finally, well, not finally, the fourth one is the ground floor insulation. At the very top level of the building, adding basically some insulation material that will reduce by 5% in this case the energy consumption, and 36.6 if combined with the previous one. Once again, we consider this aerogel insulation board to be added to the ground floor of the building. And last but probably most important will be the air-to-water heat pump. So basically we are completely replacing the boiler and placing either indoor or outdoor units of, in this case, you can see that there are both indoor units or outdoor units. For traditional buildings, if there is a space indoor, that's ideal situation, because it's not great looking, the outdoor unit on a traditional facade. And basically we are bringing the coefficient of performance to 3.25 from the previous one, which was lower than 1, obviously, with a traditional boiler. And basically all the natural gas consumption, as you can see, it's disappeared because we are switching to a heat pump. So all the consumption is now electricity consumption. And you can see that it's obviously higher than before because we are heating now the building through the electricity, but we completely got rid of the natural gas consumption. So we have a huge saving of 48.5%. But as you can see here, it's not ideal to consider this solution without previously improving the building envelope, because with a very leaking building, let's say this solution of heat pump will not be ideal. So ideally this is something to consider only if combined with a good improvement of the building envelope first. And altogether the deep renovation measures will bring to 56% of combined reduction in total energy. If we have a look at a summary of what I just talked you through, the green one here, it was the baseline energy consumption from the model. The single measures, so the operational ones, or the shallow retrofit measure, or the deep renovation measures, will bring to these three values. So as you can see, as we expected, there is quite a good saving with operational, better saving with shallow, and huge saving with the deep renovation. While the combined measure will be 113 kWh per meter square if combining operational plus shallow retrofit, or combining all of them together, so all operational, shallow, and deep renovation measures, we will go down to 64 kWh per meter square per year, which is a very good value for a traditional building. So this is just a summary of all the interventions that we considered, and you can see that we considered these interventions to all the 5 buildings. Obviously not all the same interventions. For example, if you look at this commercial building here, this was already a LEED certified building, so there was really almost nothing, not only that they could, but that they wanted to change to the envelope of the building, because obviously it's just being built, so they are not willing to replace anything, and it's not reasonable to do it. So this 3.6% of savings were coming from the operational side. So even if there was a LEED building, still on the operational side, there is always something that can be done to improve the energy consumption of the building. While the other buildings, you can see they are all about 60% more or less of possible reduction with different measures, because not all the same measures can be applied to different buildings, as I said in the beginning of this. So you can see that now we have values for all the 5 buildings. So these values here are for the whole positive energy block, which is not positive yet, but that's the aim goal. So basically, 1.57 gigawatt hour per year was the initial consumption of the block, divided into 0.6 of natural gas and a bit more in electricity. After the interventions were conducted, we went down to 1.2 total energy consumption in terms of gigawatt hour per year. This is still like quite high, if you notice, compared to the fact that in the previous slide I mentioned that 60% almost on every building was reduced. This is because that commercial building is basically huge. So one gigawatt hour is basically only coming from that huge building, which, as you saw, wasn't reduced much because it's already good, well performing. But it's important to, we didn't want to get rid of that building only to have better results, because it's important to understand that when you select a city block, there will be building, new building, old building, and it's important to understand how they can interact with each other. So it was important for us to anyway keep that building in the analysis. So the next step will be how now from this 1.2 gigawatt hour we can reach zero. We need to integrate, we need the integration of renewables that come always after the energy intervention to the building, because if we just apply photovoltaic panels to a building which is performing very bad, it's not an ideal situation. So we studied the possibility of adding photovoltaic panels to the roof of all these 5 buildings, obviously not the whole roof, but depending on the available area on the roof. And we use the IVN, as you can see here, is our intelligent virtual network, which was able to take the simulated values for energy demand of the 5 buildings coming from the VE and basically simulate what will be the added value of solar potential on the roof of these 5 buildings. After doing some quick simulation, we were able to basically understand that there is quite a good production that can be retrieved during the summer months. Obviously, on a monthly picture like this, it's not always ideal to run a simulation and just say, oh, okay, my demand is higher than my generation, so I'm not wasting any energy. That's usually what's done in a very simple and quick PV and solar analysis. But actually, thanks to the tool, we were able to do this at a hourly level. So if we look at things at a hourly level, we can see that actually the blue line, which is the electricity generation, in some cases, for example, here, if I'm not wrong, it's a weekend, a Saturday and Sunday. Basically, it's producing more than these 5 buildings are generating more energy than what they are needed to run. So we are actually wasting energy in these particular times along the year. And at the end, it's a matter of trying to understand how much these values are along the whole year. And eventually, we could consider adding a battery storage, an electricity storage, for example, like a battery, if that expense is justified by the fact that we are wasting a lot of energy. When I say wasting, basically, it means that we are producing more than we are generating. So we are just giving back to the grid, and it's not always that easy to sell back to the grid. It really depends on the country and the regulations. So you can see that the total production will be about 196 megawatt hour per year, but the useful one is 175. So basically, we are wasting about 20 megawatt hours per year. In this case, it's not that big, so it doesn't justify installing a battery, but in other cases, it could. So the electricity demand of the block went down from 800 megawatt hours per year to about 615. And you can see that basically the intelligent virtual network is not only able to simulate the photovoltaic potential, but we could insert other assets like wind turbines, electricity storage, electric vehicles, and everything that you could need to consider going through the possibility of building a smart district, a smart block, a smart city. Basically, after this improvement, so we were at 1.2 gigawatt hour totally electricity plus gas consumption minus the production from PVs. We are at about 1 gigawatt, and then we considered the addition of other arrays of photovoltaic panels, not on the roof of the buildings, but on a field nearby that block, added to a tidal turbine. So this is basically a mixed field of photovoltaic panels and tidal turbines that are running together and are able to produce about 1.2 gigawatt hour per year. And we reached a positive annual balance of about less than 0. So we are actually producing more than rather than what we are consuming, thanks to this final installation here. This was the last, let's say, summary slide, and I will very quickly show you something else here. Let me share my other screen here. So basically, we decided to bring this live on a dashboard that basically is representative of the model that we did, so that, for example, the city itself, or in the future the citizen, through touch screens, will be able to interact with the model and see how their building is, for example, performing compared to the others. So, for example, this is an interactive model that I can just zoom in, zoom out. I can click on a building and see all the properties of that specific building, and all of these buildings are simulated. So, for example, I saved some scenarios here. For example, if I want to look at the energy consumption of the building, and here I have all the color scheme that I can change, and you can see here there is basically a bar that it's explaining the results. Or I can do the same in terms of CO2 emissions, and once again I can click on the metric and see an explanation of the results. If I then zoom into the positive energy block A, you can see these are basically the 5 buildings that we did the models for. So if we click on a specific building, we can see here also a summary of the energy model, and we can see all the results in terms of simulated data, like the electricity data, and also like all the time series channels of simulated data or meter data, depending on what we want to see here. The idea is that this interactive model will help people to go through the model and see how their building is performing, eventually giving feedback if their building hasn't been modeled perfectly, so we can fix the model. And you can see these KPIs here are basically a summary of the natural gas and electricity consumption currently of the building, and the annual renewables only taking into account the PVs placed on the roof of those buildings. There is interactive graphs on the natural gas consumption of the last 12 months, and the same on the electricity. The dark blue you see that basically is the current one, while the light blue is instead the one if we applied the energy conservation measures, so the operational, shallow, and renovation measures. The same style is about the solar production. You can see here, once again, here I'm displaying the last week values, so the simulated values for this week up to today, you can see. And it was a week and a couple of days ago, so the generation was higher than actually the demand of the building. If you would like to see a different display, for example, you can say, okay, let's display the last month. All these data are coming from the iScan platform. So all this is basically live data stored in there. So this dashboard is not just a picture, it's actually displaying data that are coming from the platform. Then there is the actual energy balance, and the energy balance with the applied interventions. Here we didn't consider the last interventions that I mentioned on renewables, because that's the next step, and the saved carbon emissions. So you can see this block saved a lot of carbon emissions every year, but it still needed about 1,000 megawatt hours per year reduction to reach a positive balance. So yeah, this was just to show you a possible way of then displaying the results, because a presentation could be something that from a technical perspective is efficient, but when you then start to engage with people, to engage with local communities, it's very important to understand what's the best way to engage with them, and they most probably are happier to play with the model like this rather than to just look at slides that maybe they can't understand from a technical perspective. Going back to the last slides, I think that was the last one. Just let me go in presentation mode again and see if yeah, and this is called the ICL, which is the Intelligent Community Life Cycle, which is basically the summary of all our tools that I've shown during the presentation put together. So the V, the iScan platform, the IVN, all these tools are together into the Community Life Cycle platform. And thanks for listening to this. I don't know if Ruth has anything to add to what I said. Otherwise, we will start looking at some of the questions. Okay, let me go here in the chat. Okay, here there is a question from Jess. What assumptions were made regarding the power consumption of the LED lighting controls? So basically, all the assumptions there, well, the consumption, the internal gains and consumption in terms of watt per square meter of the lighting, either fluorescent or LED lighting, were coming from manufacturers, while when you mentioned the parasitic power from the lighting controls, there we looked into some possible solution from manufacturers. So basically both the cost estimation that actually wasn't in this presentation, but both the cost estimation and the parasitic power was coming from manufacturer values. Now I don't mention the specific manufacturer, but they were coming from data sheets and average consumption values from the manufacturer. Let me see here. So there is a question on the machine learning algorithm that was used for the natural gas consumption extrapolation from the utility bill. So basically, this really depends on on various factors. So first of all, the weather, so where your building is. Obviously, depending on the building type, the location, and other factors, you need to create an algorithm that is like mostly representative of the main factors that could influence your gas consumption. Obviously, there will be so many factors to take into account, but you need to consider the, let's say, the most effective ones that in this case for the particular location of the building and for the information that we had also, because sometimes you don't have all the information that you would like to. We consider the outdoor temperature and the heating degree days and also the schedule of the building to, let's say, create a machine learning algorithm. So there is not, the answer is, there is not one machine learning algorithm that will solve all your issues, but if you go on to explore that field, then it's a, let's say, a case study by case study understanding on what the most effective variables will be. Yes, the carbon factors that are used for the calculations are coming from the SEI values from the Irish standards. So yes, that's another important point, that when actually you are modeling in a specific region, in a specific country, it's important to take into account what are the carbon factors of that specific region, and also eventually, now we were looking at final energy, but also if you want a full picture, you would also need to look at the primary energy factors of that specific location, which might guide you through the use of different sources. You could start considering biomass, you could start considering natural gas or any other source, depending on what's actually the primary energy factor of that particular location. So in this case, it was Ireland, and those Irish factors were used in the calculation. Yes. Yes, the weather file that was used was a weather file that was taking into account, yes, all the solar insolation of the site, including the shading from the nearby objects and nearby buildings. So yes, for the photovoltaic panel operation, all that shading factor was taken into account. And you're asking also, Salman is asking also other factors like rain and snow. These factors are usually factors that are already being considered through a factor within obviously the weather file doesn't simulate the effect of rain on the photovoltaic panels or the effect of snow. So these additional factors are factors that can be put into the calculation as a, let's say, overall inefficiency factor, that usually there are calculations that and estimations to calculate that for specific regions. Also suggestions from the manufacturer itself, because obviously the model won't simulate the rain or the snow on your panels, but you can take that into account through so-called inefficiency factors. So Konstantin is asking how you calculate heat losses and U values through the ground floor, because heat losses depend on the type of ground and the U value is affected by corners and center of the floor. Yeah, that's a good point. So basically the U value that I've shown there was the U value of the floor itself. Then the model will also consider basically thermal bridges within, like from the ground floor, like at the corner between, for example, the ground floor and the internal wall, or the ground floor and the other wall. The software will take into account the thermal bridge, but the U values that I've shown was only for the package of the ground floor. And that's exactly the reason why I said that with deep renovation, the idea of having multiple benefit from additional renovation is exactly here, because once you are insulating the floor but you are not insulating the wall, you will still have a huge thermal bridge there. While if you are doing both, you are also going to take care about insulating that corner between the ground floor and external wall. So in this way, you are actually also addressing not only the U value of the single element, but also the thermal bridge there, so reducing the overall heat losses on the in the building. And this obviously the thermal bridge is calculated by the software. Once you replace both the ground floor and the wall, then also your thermal bridge, you will reduce your thermal bridge as well. And that's influencing a lot the thermal losses, the heat losses. Is the cooling load optional consideration, and are there options for modeling steam production usage for commercial buildings? Thanks for asking. So in this case, the cooling load was not considered for the particular location of the building. There is no cooling at all in this particular site, so that's why the cooling load, we didn't see anything on the cooling load. But I won't say it's an optional consideration. It's something that must be considered if you do have the cooling load in your particular building, whether it's a commercial building or residential. So yes, definitely you do have to consider that. And for modeling steam production for commercial buildings, where you are not well, you are actually modeling the steam production, not as steam production, but basically you are modeling the heat gains, either as sensible or not sensible heating gains. So in that case, you will model within the model, if you have a particular commercial appliance, then you will need to understand what's the sensible heating load coming from that. And you will input that to the model so that it will automatically create a heat gain that then you will then need to reduce through cooling loads. If that particular room needs to be cooled at a certain set point, for example, a data center or whatever, then yes, definitely you can insert that appliance heat gain in the model, and according to the set point that you set as a maximum temperature, then your cooling system will operate to reduce that steam production. Okay. Regarding the U value of the double glazing as well was taken from the from construction manufacturers, and we selected the double glazing because we found a possible let's say solution in Ireland for replacing existing windows without, let's say, touching the frames or retaining the existing frame and just replacing the window pane. So that's why we selected that particular window, and the U value of the new window is only related to the pane itself, because obviously the manufacturer won't be able to give you a U value of the window plus the frame without knowing what frame is in there. So usually they only give you the U value of the glazing itself when you are not buying a full solution. So yes, that U value is representative of the window, and then it will need to be averaged with the one of the frame. And just the last one that I noticed here, were the unregulated loads considered in the modeling? When we have carried out operational energy modeling in the past, we have found this to be quite a significant factor. Okay, that's an interesting statement as well. Yes, basically, this is why once you start creating your baseline model, obviously every energy modeler starts from, okay, let's first build the geometry of the building and let's use the standard loads for that particular building, either coming from ASHRAE loads, either coming from CIBSE standards, or whatever standard is used in that particular region. So the unregulated loads obviously are something that are above that standard. That standard won't take into account if in your building, for example, if you have I don't know, just a stupid example, if you have an office and you have 3 fridges in a small office, obviously the standard won't take that into account. That's something that you as a modeler need, if you have the possibility to do. You need to go into the building itself or try to speak with some facility manager or anyone who is occupying that building and try to retrieve as much information as possible, not only as what's actually in the building, so if there is some appliance that is unexpected or that is consuming higher than the standard, or either something in terms of operational, on the operational side. So for example, if a school as the one that we just saw is operating outside the normal hours of a normal, let's say, average school, so it's not just 9 to 6, but it's actually having events during the weekend, during a particular night, all these additional loads, or even plug-in loads, if there are, I don't know, students that every day go and plug in their laptop, this is something that makes a huge difference in the model. So it's something that needs to be considered by surveying the building, by talking with the facility manager, by talking with whoever can give you that particular information on the building. And this, yeah, definitely will give you a much better picture of how the building is operating. And that's probably one of the reasons why in that particular month in May, we saw that the energy model was not representing the building, but the building was consuming way more in May rather than in April, for example, where you expect a bit more heating load during April. So probably in May something happened, and that's exactly the case where you start comparing your energy model to your utility bills, and you start asking yourself, why is actually this happening and why it's not reflected in my model? And that's exactly when you start retrieving that kind of additional information. And the answer could be there is a problem in the model, or it could be there is a problem in the building. So did they leave their lights on for a whole week? And that's also the potential of the dashboard, which will be able to show you live data from the energy meters, so that someone will understand that the lights are on not after a week, not after a month, but after 2 hours, 3 hours, or wherever they want to set up the alerts saying, actually, look, you have an energy model that is saying you're supposed to consume 100 kilowatt hour per meter square, you're consuming 110, 20, and 110. So you can set up alarms after let's say, after your actual meter is going too far from the simulated values. So that's the potential of it. With this, yes, I will conclude this webinar as we are 20 minutes past. Almost. Thanks for joining this. Thank you. Goodbye.